In this episode, we're going to build a practical way to recognize what malicious code is trying to do, even when you don't know the name of the malware or the specific tool an attacker used. Beginners often imagine malicious code as a single bad file that gets detected and removed, but real attacks behave more like campaigns, where the attacker's code must enter a system, stay there, avoid being noticed, and then expand to reach more valuable targets. If you can describe behavior in those stages, you can reason about risk and response without needing to be a reverse engineer. The 4 behavior themes will focus on our infection, persistence, evasion, and lateral movement, because these show up across many types of malware and attacker techniques. Understanding these themes also helps you avoid common misconceptions, like assuming that if a machine still works normally, then it must be clean, or assuming that encryption or antivirus alone will prevent compromise. The goal is to give you a clear, beginner-friendly model that makes malicious behavior recognizable as a pattern of objectives rather than a collection of scary headlines. Infection is the first stage, and it is best understood as the moment an attacker's code gains a foothold in a system that was not supposed to run it. Infection can happen through many routes, but conceptually it always involves a trust decision being abused, such as a user opening content, a system accepting input, or a software component executing something that was not intended. Some infections rely on social engineering, where the attacker convinces a person to run something dangerous, while others rely on exploitation, where the attacker triggers a flaw in software to execute code without the user knowingly approving it. Beginners sometimes treat these as totally different worlds, but the outcome is the same. Code that the defender did not authorize begins running. It's also important to understand that infection is often not a single event, because attackers may first gain a small foothold, like a script that runs briefly, and then use it to pull down more capable components. The initial infection may be lightweight and hard to notice, while later stages bring more durable or feature-rich malicious code. Recognizing infection, therefore, means paying attention to abnormal execution paths and unexpected processes, not just looking for one suspicious file. A helpful way to think about infection is to watch for mismatches between what a system should be doing and what it is actually doing. For example, if a document viewer suddenly triggers network connections, or if a browser session results in new background processes, those mismatches can be clues that the initial content did more than it should. Another infection clue is when normal user actions produce unusual prompts, unusual errors, or unusual requests for elevated permissions. Attackers often try to blend in by making their content look like something the user expects, such as an invoice, a resume, or a shipping notice, because curiosity and urgency create shortcuts in judgment. Even without getting into technical details, you can understand the defender's challenge. The system has to make decisions about whether code should run, and attackers are constantly looking for ways to make malicious execution look normal. Infection is therefore partly a technical problem and partly a human problem, because humans are the ones who interpret what looks normal and decide to click or approve. A strong security mindset tries to reduce unnecessary execution paths and to make suspicious execution stand out. Once malicious code runs, it often tries to establish persistence, because attackers rarely want access that disappears when the system reboots. Persistence is any mechanism that ensures the attacker's code will run again later, either automatically at startup or triggered by a particular event. Persistence matters because it turns a one-time infection into ongoing access, giving attackers time to explore, steal data, and plan their next moves. Beginners sometimes assume that rebooting or closing a program will remove malware, but persistent code is designed specifically to survive those actions. Persistence can take many forms conceptually, such as placing code in locations that run automatically, modifying system settings that cause future execution, or embedding itself in components that are loaded regularly. The behavior signature is that something is arranging to run again without the user explicitly choosing to run it. In other words, persistence is about installing a habit into the system. Persistence often comes with an operational goal: keep access stable while reducing the chance of being detected. This means attackers may choose persistence methods that look like legitimate system behavior, such as using names and locations that resemble normal components or tying their execution to common tasks. They may also build redundancy, meaning more than one persistence method, so if one is removed, another brings them back. That redundancy is a major reason malware removal can be difficult, because you can remove one visible component and the hidden backup restores it. Another persistence trick is to avoid writing obvious files and instead to store code or configuration in places defenders don't expect, making it harder to find. For beginners, you don't need to memorize specific persistence mechanisms to understand the concept. You just need to recognize that if an attacker wants long-term access, they will create a way to re-enter the system without repeating the original infection path. When you see repeated suspicious behavior after cleanup attempts, persistence is often the reason. Evasion is the set of behaviors that help malicious code avoid being detected or blocked. Evasion is not a single feature. It is a strategy of reducing the visibility of malicious actions and increasing the cost of analysis. Some evasion focuses on hiding the code itself, such as encrypting or packing it so signature-based detection struggles. Other evasion focuses on hiding behavior, such as delaying execution, running only under certain conditions, or blending network traffic into normal patterns. Attackers may also try to detect whether they are being analyzed and change behavior accordingly, which means the code behaves differently in a controlled environment than it does on a real target. A beginner misconception is that evasion requires advanced stealth technology, but many evasion techniques are simple and effective, like using legitimate tools and normal system processes to perform actions, which makes malicious activity look like ordinary administration. Evasion also includes the human layer, like using believable lures and creating fake urgency so users ignore warnings. The core idea is that evasion exists because attackers know defenses are watching, so they design their actions to be less obvious. One of the most important evasion concepts is that malicious code often tries to reduce the number of clear, high-confidence signals it generates. Instead of doing everything at once, it may perform actions slowly, in small chunks, or at times that look normal for the environment. Instead of contacting a suspicious server directly, it may route communications through common cloud services or through domains that look legitimate. Instead of dropping a large, obvious file, it may use small scripts and built-in components that are already trusted, which can bypass simplistic allow lists. This is why modern defense often focuses on behavior patterns and context rather than relying solely on known bad signatures. For beginners, the takeaway is that you should not assume the absence of obvious alerts means the absence of compromise. Evasion is a deliberate design goal, and attackers are often successful at staying quiet long enough to reach their objectives. After infection and persistence, many attacker campaigns aim for lateral movement, which means expanding from one system to others in the same environment. Lateral movement matters because the first compromised machine is often not the most valuable one. Attackers may compromise a user device first, then use it to reach file shares, internal services, administrative systems, or domain controllers. Lateral movement is essentially an attempt to turn one foothold into broader access, and it often relies on stolen credentials, reused passwords, or overly broad trust relationships between systems. Beginners sometimes imagine attackers jumping magically between computers, but most lateral movement is more like normal access abuse, where the attacker uses the same pathways legitimate users and administrators use. That's why least privilege, segmentation, and credential hygiene are so important, because they determine how far an attacker can go from the first machine. In lateral movement, the attacker is looking for doors that are already open, not just trying to smash through walls. A key lateral movement behavior is discovery, because attackers need to learn what exists and what is reachable. Once inside, malicious code or the attacker's tools often scan for hosts, list shared resources, look for cached credentials, and map relationships between accounts and systems. This is not always noisy, because attackers can perform discovery slowly or focus on a small set of targets. The goal is to find systems that contain valuable data or provide higher privileges, and to find routes to reach them. Lateral movement can involve remote access protocols, file share access, service calls, or administrative interfaces, but the common thread is that the attacker is using internal connectivity that was never meant to be a free-for-all. For beginners, the behavior level lesson is that if one system starts reaching out to many others in unusual ways, or if accounts begin authenticating to unusual systems, that may indicate lateral movement attempts. It's about unexpected internal spreading behavior rather than an external internet connection alone. Lateral movement also connects strongly to the idea of privilege escalation, even though we are not making it a separate headline today. Attackers often need more privileges to access protected systems, and they try to obtain those privileges by stealing tokens, capturing passwords, or exploiting misconfigurations. Once they gain higher privileges, they can move more easily because the network treats them as trusted administrators. This is why credential theft is often the hinge point between a minor incident and a major breach. Malicious code might start with the permissions of a normal user, but its goal is often to become an administrator because that unlocks access to many systems and makes detection harder due to the legitimacy of the account. A beginner-friendly point is that identity is the currency of lateral movement. If the attacker can obtain credentials that the environment already trusts, they can move in ways that look like normal activity. These four behavior themes also show up differently depending on the malware's objective, which helps you interpret patterns. Ransomware often prioritizes rapid spread and broad impact, so its lateral movement and encryption activity may be loud and time-compressed. Espionage-focused malware often prioritizes stealth, long-term persistence, and quiet data collection, so its evasion and persistence behaviors may be more subtle and its lateral movement may be carefully targeted. Credential-stealing malware often focuses on capturing authentication material and then using it to access other services, which can look like unusual login behavior rather than obvious file changes. The point is not to memorize categories of malware, but to recognize that the same stages apply even when the pace and style differ. Infection, persistence, evasion, and lateral movement are like a set of strategic goals, and different attackers emphasize different goals depending on what they want. When you see behaviors, you can ask, which goal does this behavior serve, and what might the attacker do next? To close, spotting malicious code behaviors is about understanding the attacker's objectives across the lifecycle of compromise. Infection is the foothold where unauthorized code begins executing by abusing trust decisions in people or software. Persistence is the habit, where the attacker ensures access survives reboots and time. Evasion is the camouflage, where the attacker reduces detection by hiding code, delaying actions, and blending into normal system behavior. Lateral movement is the expansion, where one compromised system becomes a stepping stone to others through credential abuse and internal trust pathways. If you can think in these stages, you can interpret suspicious events more clearly and connect them to defensive priorities like strong authentication, least privilege, segmentation, patching, and monitoring. This behavior-based view also keeps you from overreacting to brand names and underreacting to subtle signs, because it focuses on what the code is trying to accomplish. Once you see the pattern, you can ask better questions, anticipate likely next steps, and respond in a way that reduces damage rather than chasing symptoms.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.